Okay, we're going to talk about thin film interference. Okay, so the idea is that a thin film is some material. Okay, it could be liquid or solid. It's some thin material where a light can travel through it. So it's optically transparent. Okay, or at least somewhat transparent. And the question is, what happens to the light as it goes through this material? Or what we'll see is bounces off the material. So the light will reflect off many materials, and in fact, nearly all materials, it'll reflect at least somewhat off of it. And so you can imagine a ray of light coming down, it hits this front surface, and some of it reflects off. Okay. It's going to go like that. All right. Some of it goes through. You know, if you look through a soap bubble, you can see through the soap bubble, but you also see colors off the soap bubble. So some of this original light goes straight through it. Okay. But then that light hits the next interface, and some of the light reflects, and some of the light goes through. Okay. Right. Now this ray, some of the light reflects, which we won't worry about, but some of that light goes through. So we've got all these different rays because of these multiple reflections and transmissions. Okay. Now, what's really interesting is if we're standing over there looking at these rays enter our eyes, well, we could see them interfere now because they're the same source. And so they could be constructively interfering or destructively. It all depends on how the wavelengths overlap here or what the phase is in this region. And that's going to depend on two things. Okay? The first one, kind of the most important one, is that the ray that came out here traveled an extra distance of this much. Now, I've drawn it at an angle like that just so we can see it. But the analysis we're going to use is assuming these are pretty much straight down and straight back out. Okay, but if I drew that, we wouldn't be able to see it. So when I say this traveled from here to here, I'm really just saying it's traveling the straight line distance, and I'm going to call that D. Okay, so it travels a distance D down and a distance D back up. So because this ray that came back out had to travel an extra distance of 2D, then it could be out of phase from the original one, or it could have gotten back in phase, as long as that distance was some multiple of a wavelength or some multiple of a half wavelength. So if it's some multiple of a half wavelength, then they would have been out of phase. If it's some multiple of a full wavelength, they would have been in phase. Okay. So if I'm looking down and this is green light and I see green light reflecting off really strong, or maybe the rays coming in is white light, so all sorts of wavelengths. Okay, but I see green light really sharply. I see a lot brightly, I should say. I see a lot of green light. Well, that means this thickness here was just right, so that the distance, extra distance traveled, must have been equal to a wavelength or a multiple of wavelength of green light, and all the other ones weren't. So the other colors disappeared. They reflected destructively. Okay. So we can use the color we see, to be able to determine the thickness of this film, which is pretty cool because since wavelengths of light are really small, hundreds of nanometers, we can measure films to hundreds of nanometers. That's a pretty good measurement technique. Okay, so how are we going to do this? The goal is that the path goes down and back up. So the path difference, and you say that's delta R, is going to be 2D, all right? And we want that to be equal to either a wavelength or 2 wavelengths or 3 wavelengths or 4 wavelengths, okay? If we want constructive, okay, if we want them to add together to be bright, or we want it to be equal to a half wavelength, if we want it to disappear or be destructive. Because if this total path difference, 2D, is half a wavelength, then it's going to come back out flipped by the time it matches up with this one and combines into our eye. All right, so that's the condition we have here. That's one condition we have, is the path difference, which is 2D, is either a wavelength or a half wavelength, depending on the condition we want. But there's another feature here that's really subtle, but really important, okay? Light, just like a string, has different effects based on how the boundary. So for example, when I whip a string, if it hits a fixed point, it gets inverted on the way back. Okay? But if I flip a string and it hits a loose point, it will stay upright on the way back. The same thing applies with any wave. If the light travels into something that I would call optically heavier, okay, or more massive, like the fixed point, it reflects, it flips by half a phase on the way back out. So if I were to draw this a little more carefully, if this was going like that, then it would have hit that point, and this reflected one would have flipped around to go out the other way. Whereas here, the transmission point would have just kept on going. So the ray that transmits keeps on going, the ray that hits and bounces off flips. Okay. So we have to keep a track of how many times they flip. So for example, if this is air, so if we suppose that's 1, because that's air, let's suppose this is some oil, okay, maybe about 1.2. All right. So it's optically heavier in that sense. Its index of refraction is higher, it's sluggish, the light slows down. So that means this ray is going to flip. We're going to get a pi phase change at that interface. Okay. All right, now let's just suppose that this one is even heavier. This might be water. Okay. Well, that means this ray is going to flip as well. And so we're going to get a pi. Here, let me do it on the top side to emphasize the reflection. We're going to get a pi phase change on that ray. Okay. And so it's flipped too. And it comes up here, but it transmits, and no transmission ray, no matter what boundary, ever flips. It stays the same. So now they've come out on top of each other again. So like if I were to draw this, it's going to get a little complicated. So that flipped. This one also flipped, but it just kept on going as it came through. So now they're in phase with each other, where here I've assumed that this thickness here was 1 wavelength. So twice the thickness is 2 wavelength. That still matches our condition. As long as it's a multiple of a wavelength here, an odd multiple of a half wavelength. Okay, so here I've drawn the case where it is constructive. All right, but I had to be careful because there was a phase change there and a phase change there. Those 2 phase changes basically said, oh, I can ignore the reflections. I can ignore the phase changes at the reflections. Okay, and just think about the path difference. But what if we reverse this and make this air again? So like a soap film sitting in air, just a soap film just on a bubble. It's sitting in air. So now this ray that comes down here, I'm going to have to erase some of this stuff. Let's clean this all up in here. This ray comes down, this ray goes up, keeps on going. All right, so this one keeps on going. All right, gets there. But now it bounces off a smaller index of refraction, which is like a string bouncing off a free end. And so it comes back upright. So that means it's going to go like this. Okay. And then it comes out, transmits. And look, now they're out of phase. Those waves that are coming out are out of phase. So because of that, our path difference, though it was a multiple of wavelength, here I've drawn 2, or the the thickness is one wavelength, so twice the thickness is twice the wavelength. And though that's a condition for constructive, we got destructive because we had the additional pi or half a cycle flip because of the reflection. Okay, so we have to keep those in straight. So a way I like to do it, because that's pretty complicated, lots of stuff to think of. You can write out an equation. You can talk about that, your delta phi between the two is going to be a 2 pi delta r over the lambda. And we need to be careful. It's going to be the lambda in the material, okay, not the lambda outside, okay, over the lambda plus any delta phi. I'm going to put bound for the boundaries, the reflections, what happens to the reflections. So I have to think, okay, what happens? In the first case, we had pi plus pi, because there's two reflections of pi. And so we got 2 pi. Oh, that doesn't matter now. In this case, we have just 1 pi, so there's pi there. And so in order for this to be constructive, this would have to be pi or non-multiple. So you can do that if you want to. This is a great way to use our math to do that. But it's much easier to think conceptually. Just break it down, compartmentalize it. And think, okay, before I consider what's going on, let's just see, do I have any phase changes? Okay. If I have one phase change at the boundary, then I flip these rules. And then I just look at the thickness. If I have 2 phase changes at the boundaries, then I just look at the thickness and keep these rules. So that's the best way to look at it, and it's a much more logical way to think, or keeping the physical nature of the problem there instead. But again, the math works just fine too. So that is how you'd find a thickness of a film. We can now just relate this to what wavelength we have, and you're remembering it's the wavelength in the material, and decide on what our condition is with its boundaries.